Okay, today we're going to talk more about the atomic orbitals, in particular node analysis. So this will be a way to really understand the nature of the nodes and how that can help us understand what these atomic orbitals look like. So the important spots on the atomic orbital are to identify the nodes, and we've noted that if the sign changes from plus to minus or minus to plus across one of these lines, then that's representing the node in three-dimensional space. Now, the outer line, or the outer curve here, is not representing a node, because if this is plus, this is still plus out here. It's just fading away. And so we do not have a node being represented by this outer curve. So the nodes themselves break into two types, radial nodes and angular nodes. So a radial node is if you take your pencil, go to the nucleus, and draw in any direction. How many nodes do you cross? So in this case, we cross a node here, and this would be true everywhere. You do want to avoid a degenerate case where you go right along another node. So you don't want to go along another node, but just take some sort of typical ray coming off of the nucleus, and how many nodes do you cross? Those are called radial nodes. Angular nodes occur when you start at the bottom and go 180 degrees. Well, not necessarily the bottom, but just anywhere, and you go 180 degrees. Again, you don't want to start exactly on a node. So we start out here, we go around, and we ask ourselves, did our sign change? Well, it did right here, because it was negative down here. When we get up here, it's positive. So it's negative, positive. So we have a nodal plane right here, and we call that an angular node. So you want to be able to identify whether a node is radial or angular. The total number of nodes is going to be the angular plus the radial number of nodes. And there's always going to be n minus 1 total nodes. And so if n is 4, then we know we have 3 total nodes. We don't necessarily know what type, radial or angular, but we know there's 3 of them. Now, if we know the shape of the, or if we know the L value, then we know the number of angular nodes. Angular nodes number is always equal to L. And thus, if we know the N number and the L number, so if we said something like a 4F orbital, then we would know both of these, and thus from this we can get the total number of radial nodes, which is N minus 1 minus L. Okay, well, let's walk through some of the atomic orbitals we already know, and then let's talk about where the nodes are placed, and then we'll just do a little bit of practice. So let's try a 2s right here, 1 radial node. So this is what we're doing here is called node analysis. So let's do this. So radial node equals 1. Angular node, right? I'm minus. Angular node equals 0. Total nodes equals 1. So there we use the picture, and we just counted the appropriate types of nodes. Now let's see how this matches with the label. Well, n is 2, so 2 minus 1 equals 1. That's the total nodes, right? N minus 1 total nodes. L is S, that's 0. So angular nodes is 0. That works out, and so the radial nodes work out. Okay. So that would be the node analysis of this. Let's look at this one, 4d x squared minus y squared. Well, I'll start here at the center, and I'll work my way out, and I get 1 radial node. And this would happen if I go in any direction here. So radial node equals 1 here. Let's do angular nodes. I'll start here. Now here I'm plus, here I'm minus. So I have a node here, and then so all along here I'm plus, now I'm minus, and then I'm minus here, but here I'm plus. So as I cross here, I'm minus to plus. So I have 2 angular nodes. We add these up, total nodes, 3. So from the picture, I did the node analysis. So now can we get the right label? Well, total nodes is 3. So this implies n equals 4, which is what we have. This is a 2. So S is 0, P is 1, D is 2. So this says we're a D. So we're a 4D. Okay, well, what about that? What about that? So let's take a look at these subscripts and see what they say. So what you do with the subscript is you take that subscript and you set it equal to 0. And so here, for the PZ, we get Z equals 0, and that defines the nodal plane. The node is where it's 0. That defines the node, whatever that shape may be. So here, it's a plane, because if we look at the 3D coordinate system, the Z equals 0 is the XY plane. So this implies the XY plane. And so the node lies on the XY plane. Therefore, the lobes are above and below, plus minus, which is precisely the 2PZ picture that we have. Okay. So you take the subscript, set it equal to 0. Let's look at a different one. Let's look at the 3D XY. Okay. I'm going to set this equal to 0. Okay. Now we solve this. X equals 0 is a solution, and y equals 0. These are the two solutions. And so in the 3D space, right, x equals 0 is the YZ plane, and y equals 0 is the XZ plane. Now, normally with the D's, we put these on the we project onto the XY axes, or we project, onto one of the planes. We read which plane we project to by what we have here, XY. So let's do an XY plane. All right, so we're going to take this 3D picture, we're just going to look at it in 2D as we talked about last time. And these planes are going to become lines in this plane. So we have x equals 0. That's the y-axis. And we have y equals 0. That's the x-axis. So these are our nodal planes coming out like this and coming straight out like that. And so the cloverleaf then must look like this. For that one. Let's look at a few others. Let's look at this subscript. We set that equal to 0. So we get y squared equals x squared. And so this is solved by y equals x and y equals minus x. And so again, this is x and y are involved down here. So we'll draw this in the xy plane and draw these as lines. Well, y equals x is this line. and y equals minus x is this line. And so the lobes draw themselves now. And that's how we know that's the shape of the x squared minus y squared. So we don't need to memorize anymore. We can get that from solving where the nodes are. Before we go beyond the ones we've already memorized, let's do kind of a full-blown analysis here. Right? Now we know where to put this. So we would draw that like this. Now, n equals 3. So that implies 2 total nodes. So here we're doing node analysis in reverse. We've gotten the symbol. Let's see if we can draw the picture. L equals 1. So that's 1 angular node. So we have the dumbbell. And then radial nodes then are 2 minus 1 equals 1 radial node, which we don't have here yet. So we have to add in a concentric figure. So we add in as many concentric figures as we get radial nodes. We did this one. Let's do this one here. So let's do the full node analysis. N equals 4 implies total nodes equals 3. L equals D implies angular nodes equals 2. So therefore, radial nodes equals 1. And so and then this is telling us how to draw this. Let's confirm we have the 2 angular nodes. Yep, we have the 2 angular nodes right here and right here. And now let's get one more radial node, so we have to draw that concentrically. Then we are free to choose. If we call that plus, that has to be minus, minus, plus, plus, minus, minus, plus, all the way around. Okay, so that's how we do the node analysis. Now these have been ones we've already memorized. Let's do some others. Now we'll get a little false sense of power here. Yes, we can do everything this way, but if you haven't had any complex analysis, we might run into problems where we get some like cubic equations and other things like that where we have complex solutions and we have to interpret that. So I'm not going to go into that. So just know that this method does work just completely generally, but we're going to be a little bit confined to special cases based on the algebra that we've had so far. We haven't, I think most of us watching this video haven't had a higher level course in complex analysis. If you have, then I guess I challenge you to see how you can find the correct nodal lines in any plane, given the different possible atomic orbitals. But we'll just stick to a few. I'm going to actually go out of order here. Let's do this 5G x3y minus y3x. So let's see if we can draw this picture of this orbital. So total nodes, right, equals 4 because n is 5. This is a G, okay, so L equals 0, 1, 2, 3, 4. Okay, so S, P, D, F, G. So angular nodes equals 4. Therefore, radial nodes equals 0. So we won't have any concentric, whatever we draw, we won't have a concentric picture of it. So now we need to take this and set that equal to 0. We notice we can see a common xy in both of these. And we get that. And now we can see the solutions here. X equals 0, y equals 0, y equals x, and y equals minus x. Okay. This is all in the xy plane. Now it needn't be. There are going to be some g's where it's going to have z's in there, and then you would have to draw the 3D picture. But here we can get away with just drawing this one in the plane. So here's y, x. So y equals 0. That's here. X equals 0 is right here. X equals y is here. X equals minus y is here. And now the lobes will draw themselves. So we get this many-petaled flower here. And again, we are free to choose plus, minus, plus, minus, plus, minus, plus, minus. And that's our picture of the 5G x3 y minus y3 x. Let's look at the next one here. Let's do this one, and let's see what this looks like. This represents a degenerate case, and just like with the D's, we have the dumbbell, that one dumbbell with a hula hoop that's kind of by itself, and then all the clover leaves. That's coming from the z squared. As we go up, there's always going to be a z squared, a z cubed, z to the fourth, z to the fifth. These are all coming from the m equals 0 value for a given L. And let's just see how that pattern goes. So if we want this, we want 4, n equals 4, so 3, total nodes is 3. F is angular node is L, so F is 3, and so radial nodes 0. So again, we won't have a concentric structure here. But then we say, what does this mean here? Z3. Well, this means, yes, z equals 0, but if you're familiar with the order of a 0, you can see right away this is a third order 0. If you're not, what I tell my students is, you can kind of think of this as z equals 0, and z equals 0, and z equals 0. Right? It's a little bit stronger 0 than just this case, which is z equals 0. Right? It's a little different because it's z cubed equals 0. And so this represents a degeneracy. And how does that manifest itself out in the nodes? Well, what you do is you kind of think of, let's draw this 3D plane, or 3D axes. And kind of think of some rubber sheets, 3 of them, as many as you have here. One are symmetrically distributed about the XY plane. So if there's 3, then there'll be 3 planes here. And we don't have nodal planes anymore because we don't have 2 variables, x and y or x and z. So what you think of is that this will pinch down or pull down to z equals 0, the point z equals 0, and this will pull up to the point z equals 0, and we end up with a nodal cone, a flat plane, and then a nodal cone again. So if you're starting to see that you're not following here, not a huge deal. In terms of what you need to know now, you don't need to know the F's or the G's, but if you're interested in going further, this is the kind of thing that you think about. And so this will draw itself again. So this will be a lobe here and a lobe here, and then this plane will cut that hula hoop. So it'll be an upper hula hoop and a lower hula hoop. So this would be plus, minus here. So that would look like a split hula hoop. Maybe just to make a little simpler version, let's do the 3D z squared just to complement this. So what do we say here? Z squared equals 0. So that means z equals 0 and z equals 0. Let's do this same thing. Draw our coordinate system. Put a symmetrically two planes now, because there's two here. And then we will pull down. So imagine pinching that, like imagine it's rubber and you pinch those planes and pull it to this degenerate point z equals 0. And we end up with two conal planes with the points touching. So one's inverted, one's upright, touching. The lobes will draw themselves. So lobe here, and then the hula hoop structure here. So plus, minus, plus d, 3d squared, 3d z squared. Okay. Let me just do one last thing. If we have L equals P, the function here will be a first order function. If we have D, so L equals 2, this will be a second order function in some way. So this is x to the first power, right, to the first power, or we have 3dz squared, so a second order. Here's first order times first order, that's second order. And then, I erased it, but the f, like a z cubed, so that'd be third order. And then the g function, which was x cubed y, right? That was a fourth order function. So the order of the subscript function is going to be equal to L, always. So you can use that for a little error checking if you're gotten a picture and you're trying to go back and you have a power, you're asking yourself to get the power right, get this function right. You can check the powers as kind of a check. So the powers of each term should be equal if there's more than one term, and they should be equal to the value of L. All right, so that's node analysis. Again, here it's something just to practice. You can practice in the homework, and maybe I'll make some other videos, I'm not sure yet, with just practice problems. But at least for now, this is what we're talking about for node analysis. It's a good method to really understand these orbitals beyond just memorization.